So I actually wanted to look at something called superconductivity and something called the Meissner effect. I actually had seen a demonstration of this and wanted to figure out how it worked, which is in my purpose. And so I wanted to explain different aspects of Meissner effect and something called quantum locking, which is really cool, and of a material called superconductor. And we hypothesized that a superconductor, if it's cooled down to a specific temperature, then it's going to expel a magnetic field, which will then repel powerful magnets. So this is all the equipment we use. Here's a diagram of our setup. We are also using neodymium magnets, which are extremely powerful. One of the other things that we had to use was liquid nitrogen in order to get the superconductor cooled down to a certain temperature. And we also measured the magnetic field that the superconductor was throwing off, as well as the magnetic field of the different magnetic arrays that we had balanced superconductor on. Okay, so there's a lot of background to this. I'm going to define a couple of terms. Here is the equation for the energy of a diamagnetic material, which is defined as something that repels magnets. And in this case, superconductor, it won't allow any magnetic field to freely enter its own field because these magnetic dipoles are induced into the superconductor that will oppose the opposite field, which made this experiment. What's so remarkable about it is what happens is that the magnet will actually stick to the superconductor, but there will be a space between it. And then the Meissner effect is just the expulsion of this magnetic field from the superconductor. And the type of superconductor they used were called type 2 superconductors, which were essentially just meaning that the magnetic field that was expelled, they're coexisting alongside the superconductor in these magnetic flux tubes, which is kind of what they look like. Another thing that I wanted to point out is that we discovered something called flux pinning, which is where the magnetic field of the magnet becomes pinned or locked within the magnetic field of the superconductor once it's thrown out. And this is because when it's thrown out, there are holes in the magnetic field, so the magnet can come and lock onto the superconductor. And here we have the formula for our superconductor material, which has chemicals like yttrium, barium, copper, and oxygen. And the superconductors also make something called Cooper pairs, which are means that the current in the superconductor is carried by electrons that are impervious to absorbing energy, and in such a way that means that there's no resistance in this circuit that's created. Okay. So I have a little video of what happens. We were soaking the superconductor in liquid nitrogen. I also wanted to point out that we wrapped up the superconductor in aluminum foil so it stays, keeps the liquid nitrogen in place. So that's on there. And see, the problem is it will bounce off of the superconductor. You have to set it on there in order to get it to float. So you can see that happening here. Okay. Another thing that we want to do, we have a frictionless track as part of a superconductivity kit that was borrowed at the Science Center. And what will happen if, as you can see, one of the difficulties we had with this is that these magnets are extremely strong, and so we had a little bit of difficulty working with them. See, the tongs that we used actually got stuck to the track multiple times. And we also had difficulty like placing it directly on the track. Mm-hmm. And if you push too hard, it will fly off. So as you can see, there's no friction in between the track or the superconductors because there's space there. Okay, one of the other things that I wanted to show is that we attach a superconductor to a magnetic array, and once you turn it upside down, it's going to stay there. Gravity has no effect on this whatsoever. And this is just a superconductor. We just want to show it had the ability to spin as well. So it can do all different types of movement once it's within that magnetic field. And then here are some of the things that we observed as you saw in the video. And then I have a couple of graphs to show that we measured the magnetic field of the superconductor. And at this point is when the superconductor warmed up. This is to show that the magnetic field just reached zero. It just stopped throwing off its magnetic field. And then in our different phases that we had, there were a couple of other things. This was to show that north and south directed magnets did not have an effect on this either, and that on the magnetic field track, some of the points were positive and some were negative based on the north and south directed magnets as well. But it didn't seem to have any effect on whether the superconductor could, in fact, it didn't seem to change its superconductivity. Here, there's a couple of more graphs, just to show again that like the track with the superconductor versus the track without the superconductor, the magnetic field seemed to be the same. And so a couple of sources of error that might have happened was that we were oscillating between the superconductor and the magnetic field while measuring it. And so what we conclude from this is that we can kind of understand superconductors. Really, the math that's related to this is like really advanced calculus that my partner and I have not had. And so it also involves a little bit of quantum physics that we haven't learned yet either. And so it was a little bit hard to understand how this worked. Most of our information came from extensive research, really. And we thought they were really cool and fun to experiment with as well. And I did want to show one way to properly dispose of liquid nitrogen, since this is a semi-dangerous chemical that should be treated with carefully. This is courtesy of Mr. Lin at the Science Center, who helped us out with this experiment. You just dump it all over the floor.
It makes a fantastic sound. Would you like to turn on the stereo on the left? The button on the left of it. Power.
Over here?
Yeah. Far left of the stereo.
Is it where it says program?
No, farther left.
I mean, there's a dial on the right that says volume.
No, go over to the far left. There's a button. What do you see?
Standby?
Sure, hit that. Awesome.
Okay.
And wait for just a moment and then press play again. Go ahead.
I don't know why the sound isn't working. It makes like a whooshing sound.
Oh, it's not working. Shucks. Yeah. All right. We have time for a question.
Questions? Yes, someone?
So if you, like the track that it was floating on, if you made it so that like the track was facing itself in a circle, if that makes sense, could you like make it go around the inside and make it go really, really fast?
I believe so, yes. They're actually looking at this type of material and applying it to subway trains because it's a way to transport people without using much energy. There's no resistance.
How does the diamagnet work? Does it have a field?
It does. What happens is it expels a magnetic field that repels other magnets, but the magnetic field is imperfect and there's holes in it, and that's why the magnet is able to like attach its magnetic field onto.
How does it repel magnet? Is it charged?
It's not charged. A lot of things are actually diamagnetic. Some like examples like water, Things that just aren't naturally magnetic are considered dimagnets.
Oh, so it doesn't have to like repel magnet, it just has to be not magnetic?
Actually creates its own magnetic field that's opposite the direction of the incoming
okay.
one.
So it is charged opposite. Like,
It's you can think of it as magnetized opposite.
okay, yeah. Not opposite. Same.
But opposite.
Yeah.
Not opposite direction. Opposite direction, not opposite poles.
Yeah.
Okay.
Thanks again, Madeline.
Specific temperature, then it's going to expel a magnetic field, which will then repel powerful magnets. So this is all the equipment we use. Here's a diagram of our setup. We are also using neodymium magnets, direction of the superconductor was throwing off, as well as the magnetic field of the different magnetic arrays that we had balanced superconductor on. Okay, so there's a lot of background to this. I'm going to define a couple of terms here. And so I wanted to explain different aspects of Meissner effect and something called quantum locking, which is really cool, and of a material called superconductor. And we hypothesized that a superconductor, if it's cooled down to a really powerful, one of the other things that we had to use was liquid nitrogen in order to get the superconductor cooled down to a certain temperature. And I mean, we also measured the magnetic field. So I actually wanted to look at something called superconductivity and something called the Meissner effect. I actually had seen a demonstration of this and wanted to figure out how it worked, which is in my purpose.